Hello, welcome back. So now we are in this part, we are going to solve another beam. So this time there is a cantilever beam and we will find out the reaction because of these two loads. So as I explained earlier also, cantilever beam is a type of beam which is fixed on one end and free at the other end. So as it is fixed on one end, which means there is a fixed support, and fixed support generally offer three reactions. One is horizontal reaction RH, and the second one is RV, which is vertical reaction, and the third one is the rotation. Because you can see this force and this force, it will try to rotate this beam like this. So against this rotation, the support offer a reaction in the form of rotation itself. Okay, so this reaction will be known as M. So basically there are three reactions, RH, RV and M, and we are supposed to find out the value of these three reactions. So in the solution, again we will assume that the system is in equilibrium, assuming beam in equilibrium. And why we are assuming this? Because we have to use equations of equilibrium. So now first equation is Fx is equals to 0. So Fx is for all the horizontal forces. So there is no horizontal force. So that is why the reaction RH will be 0. Then we will use the second equation, which is summation of Fy equals to 0. Means the algebraic sum of all the vertical forces. So now we have uh, vertical forces, this one, and there is one reaction RV. It is also vertically upward. So we can write this as RV because RV is upward. I am taking this as positive, minus this force minus this force because both of these forces are downward. So we are taking them as negative 8 minus 3. And there is no other vertical force, so we will equate this with the 0. So with this equation we can find RV as 11 kilonewton. So the vertical reaction on this cantilever is 11 kilonewton, horizontal reaction is 0, and now we have to find out the value of M, which is the third reaction in the cantilever. So for that we will use the third equation, which is summation of M is equals to 0, which means algebraic sum of all the moment of forces about this beam will be 0. So I am taking moment about A. And one more thing, the reaction at point A on this beam, I am just expressing this as MA. Okay, so that there is no confusion between this M and this M. So this is MA, which is moment at A. So now I will be taking moment at A, and now we will consider the moment of all the forces. So first this force, this is 3 kilonewton, and it is rotating about point A like this, which is clockwise. So 3 into perpendicular distance. So perpendicular distance is B and A. So distance between B and A is 4 meter. Similarly, the moment due to this force, it will be again rotating like clockwise. So plus 8 kilonewton multiplied by 2. Similarly, then we have another moment reaction which is acting at point A. So now you can see moment MA is a moment in itself, and the direction of this moment is anti-clockwise. So I'm taking this as minus MA directly because this is a moment, and that is why I'm not multiplying this MA with anything. So I will write the value of moment as it is, and then we will equate this with the 0. So now solving this, we get the value of MA as minus 28. Yes, minus 28 kilonewton meter. Actually, it will not be positive. It will not be negative. So MA, the magnitude of this reaction MA is 28 kilonewton meter. So as a sign, you can see this is actually anti-clockwise. So that is why I put negative, but actually we are calculating the magnitude of MA. So MA is 28 kilonewton meter. Similarly, RV is 11 kilonewton and RH is 0. So now we have found the reaction in this cantilever beam. Similarly, we can take another example. Like in this case, there is a cantilever beam which is carrying a UVL. Now UVL is in the form of trapezoid. So you can see there is intensity 15 kilonewton per meter and there is intensity 55 kilonewton per meter. So simply, first of all, when there is a UVL on the beam, so to calculate the reaction, generally what we do is we convert this UVL into the point load. So if I divide this UVL into two area or two parts like this. So now you can see the below part, which I am referring as part 1, and the above part which I am referring as part 2. So now you can see part 1 is similar to UDL, which means part 1 becomes UDL and part 2 is triangular uniformly varying load. So now what I can do is I will be showing the same beam and calculating the area of UVL or part 1. It will be, this value will be 5 kilonewton per meter and this value will be 15 minus 5. So this value will become 10 kilonewton per meter. So this is this becomes like this. So here this is area 2 and this is area 1. So area 1 is actually referring to the UDL and area 2 is referring to the UVL in triangular formation. So we will simply calculate this area and they will be as a point load. So basically there will be 2 point load. One point load because of this area 1 and the second point load will be because of the area 2. And both will be acting at different point. Because you can see UDL is a rectangle and rectangle CG will be at the center where the diagonals will meet like this. Okay, so it means the total UDL will be acting at the center. Similarly, the CG of this triangle of area 2, it will be somewhere like this. So if this is the total length, so this point, this length will be L by 3 and the distance of point load because of the UDL, it will be L by 2 because it will be at the center. Okay, so now there will be 2 point load. One is because of the UDL, so that will be 5 into 12, which becomes 60 kilonewton. So that is the area of part 1, 5 multiplied by 12. So this becomes 60 kilonewton. So that is point load 1. Similarly, we will calculate the second one. So area second one will be somewhere here. So this value will be half into 10 multiplied by 12. So this value will also be 60 kilonewton. But this 60 kilonewton is because of the triangular part 2, and this 60 kilonewton will be because of the UDL, part 1. So now you can see this becomes a very simple problem. There are 2 point load which are acting. One is acting at the center of the length, which is 6 meter, and the second one is acting at L by 3, this one. So this L by 3 is 12 by 3. So this becomes 4 meter. So now it becomes a very simple problem. Now we can apply the equilibrium equation. applying equation of equilibrium. So we can say that summation of fx is equals to 0, RH will be 0 because there is no horizontal force. So this RH will be 0. Similarly, there will be RV and there will be MA because this is point A. So summation of Fy equals to 0, and which means there are three vertical load. One is reaction RV and two point load acting at 4 meter and 6 meter from the point A. So minus 60 equals to 0. So RV here becomes 120 kilonewton. So that is the vertical reaction. Now we have to find out the moment A. So for that we will use the third equation, which is summation of M equals to 0, and summation of M equals to 0. In this case we will take moment about A, taking moment about A. So in this case again we will follow the same 60 multiplied by 6. You can see here this load will be rotating like this. So 60 into 6 positive, plus this load will also rotating like this about point A. So this will be 60 multiplied by 4, and this direction, this reaction will be like this, and you can see this is anti-clockwise. So that is why I am taking this as MA. No other moment, 0. So MA is, the value of MA becomes 720 kilonewton meter. So that is the solution. So now we can write here as RV as 120 kilonewton, MA as 720 kilonewton meter, and RH obviously is 0. So that is the solution of this UVL. So thank you. So we will continue this topic in the next lecture. Thank you.